Hi guys, my name is Agustinus Nalwan, the head of AI and ML at Carsales.com. And today I'm going to talk about how do we scale up AI exponentially at Carsales using MLOps. Here is a little bit about Carsales. We own a portal which facilitates car buying and selling for both private and dealer. And we have around 160,000 cars in Australia, and every day roughly about 3,000 new cars coming in. And apart from cars, we also have bikes, boats, trucks, caravan, etc. And we have presence in US, South America, and South Korea. We have built and productionized many AI technology for years. For example, Cyclops car recognition, which is able to identify car make, model, and body down to the trim level from a single photo. We have Mystic. It's a regio detection model which looks for regio plate in a photo that's uploaded by a seller and blurs them to protect their privacy. We have also a lot of other AI model, such as automatic ads approval and recommendation and etc. And just to give you a sense of scale, a lot of our AI models, such as Cyclops and Mystics, are processing millions of photos daily in real time. Since 2016, our AI team has been the one responsible to build this AI tech from end to end. At experimentation, we conduct data exploration, model building and evaluation, followed by productionization step to build continuous training pipeline to regularly train the model with the fresh data and to deploy the model as a service to be finally consumed by the requesting development team. And in 2018, a new data science team is formed, which enables the second workflow where they conduct the experiment and the AI team helped to productionize their model. As the year progressed, the demand in building AI tech is rapidly increasing, which causes an issue. As both data science and AI team are small, which become the bottleneck. We need to solve this problem without hiring hundreds more data scientists and ML engineers, which won't be cost effective. The plan is, in 2022, we want to enable 2 new workflows. With workflow number 3, any software development team can pair up with data science team to help productionize their model. And with workflow number 4, any software development team can build the AI tech from end to end, from experimentation to production. As we have a lot of software developers, this strategy will give us the scale we want. So basically, we are turning our software developers into a citizen data scientist and an ML engineer. The bottleneck is not the only problem to scale up our AI. There are 2 more problems. First is the moderate effort required currently to productionize some models, especially if there is only a Jupyter notebook to work with all the chart and nodes which need to be refactored to a robust production quality code. And here is the last problem. Our data scientists mainly perform their experimentation locally on their laptop. As the current process does not allow them to easily experiment using the cloud computing due to the reliance to a limited resource of DevOps time for provisioning them. To sum it up, these are the requirements and challenges we need to solve in order to achieve the scalability we wanted cost effectively. And because we are greedy, we added 3 more requirements: flexible model deployment, model reusability across teams, and model monitoring, which I will elaborate more in the later section. And the solution which will help us achieve this scalable strategy is CIA, which stands for Carsales Intelligence Academy. It's a thin layer ML platform we built on top of Metaflow and SageMaker pipelines. CIA consists of 2 distinct components: an orchestration tools built using Metaflow, which allow us to build a continuous model training pipeline, which push the model to the deployment modules to be deployed for inference serving, which was built on top of SageMaker. So, how does the continuous model training looks like in CIA? Let's take a look at this common example. of what machine learning model training looks like. It consists of a few steps, starting with data extraction, transformation, model building, and ends with model deployment. With Metaflow, the whole process can be written as a flow, which is just a standard Python code, where each step is represented as a function with a step decorator. Any framework dependency needed can be installed by adding a conda decorator to your step. To chain steps together, at the end of a step, you simply call self.next with the name of the steps you want to execute next. You can execute more than one step in parallel by putting more than one step in your self.next call. And by adding for each and a list of jobs in your self.next call, Metaflow will execute the next step, one for each job in parallel, which is very useful for hyperparameter tuning or a large data processing without the need to spin up an EMR cluster. A flow can be run locally, which is convenient during development and debugging, and it can run in a hybrid mode where you can choose which steps you want to run in the cloud by simply adding a batch decorator, mentioning the CPU and the RAM required. Metaflow will execute this step automatically using an appropriate instance type on AWS batch within seconds, removing the need to create and wait for a Jira ticket to DevOps to be actioned. So, our experimentation at scale requirement is now ticked. To enable continuous model training, which require a scheduled and periodic training to execute in the cloud automatically, Metaflow will deploy your flow as a scheduled step function, hence no infrastructure we need to manage. Metaflow automatically archives everything you set in self.scope, which is accessible in future steps. They call this an artifact. And by loading a flow, you can access its artifact. This feature is very useful for automatically archiving our experiment, which we often forget to ensure model reproducibility. As our data scientist uses Metaflow to build their experiment, it takes very little effort now to productionize them, as we simply need to turn it into a step function in a few clicks without any modification, which ticks the box for reducing an effort to productionize a model. Now back to the architecture diagram. Let's take a look at the deployment process. And once a model is built as a SageMaker model during experimentation, deploying them for real-time inference using SageMaker Python SDK is just with one line of code. You can choose the number and type of instance to serve this model. No ML engineering skill is needed here. Hence, no doubt that any software developer can do this job. With that, democratizing ML engineering skill requirement is now ticked. What does a flexible model deployment mean? And what problem does it solve? Our previous ML serving platform only support real-time inference using an ECS cluster, which is also get called by a batch processing job, which does not really need a quick response. It causes a big problem with ECS autoscaling as it sends a large number of requests in a short time burst, which is impacting the response time of other applications which really need a quick real-time response. This is solved by replacing our model deployment with SageMaker, where you can choose a different inference type, how you are going to serve the model. Will it be a real-time endpoint when it has to respond within a fraction of a second? Or will it be batch, where application will call your model a few times a day to perform a large number of inference, but an instant response is not required? Or a serverless, when your model receives an infrequent call, but still require a quick response. Serverless utilizes Lambda, which allow you to pay only per call, which is very cost-effective compared to a real-time endpoint, which has to be provisioned 24/7. And finally, asynchronous, which is a hybrid between a batch and a real-time. With this flexibility, the requirement of flexible model deployment is also ticked. Model monitoring is an ability to monitor your model performance at runtime, the accuracy compared to the baseline, the response time, and etc. You can enable this feature for free by adding a few lines of code. And you can set up a CloudWatch alert to notify you when the model is not performing well and need to be investigated. Hence, model monitoring requirement is now ticked. Having a goal for many teams to build their AI model end-to-end raises a new challenge. How do we avoid one team building a model which already built by others? Hence, we need to allow model reusability and discoverability across teams. This is solved by using SageMaker Model Registry. At the end of the training process, the model is saved first into a centralized model registry before we deploy it for inference, which is done by a few lines of code using SageMaker Python SDK. It lets you define the instance type suitable for inference, approval status, and a description, which makes it easier for others to discover and find out more about this model. Using Amazon SageMaker Studio, any team can browse models built by others to find the one they need before deciding to build one themselves. You can drill down to a model and see the description, the approval status, was it rejected or approved, and created by who and when, providing you with a full audit trails. Adding a new status update can also be done within the GUI. It is such a useful moderation tool, and I'm keen to see a more collaboration and communication tools being added here in the future. And furthermore, you can see the location of the container used to build this model, the S3 bucket where the model is stored, the training job, and most importantly, the S3 location of the training set, which is called input artifacts, so that you can easily reproduce this model if needed. Once you find the suitable model, deploying them from the registry is as simple as executing a few lines of code. And you can choose what inference type is suitable for you. Hence, the same model can be deployed as a real-time inference by a team, but deployed as a serverless inference by others. With this, model reusability across teams is now ticked. Finally, how do we solve our last requirement of democratizing data science skill across our development team? In order to answer this question, let's revisit our architecture diagram. If you recall that the continuous model training is simply just a Python code, it is entirely then up to you how you are going to build the model, whether to use a framework like TensorFlow, PyTorch, sklearn, or using a SageMaker built-in algorithms via Python SDK. A SageMaker built-in algorithm is a collection of algorithms such as random cut forest, sequence-to-sequence, XGBoost, image classification, etc., which can be used to solve different types of problems. And they are super easy to use, as all you need to do is to prepare the required training sets in an S3 bucket and format them accordingly to the requirement. And with one line of code, you execute the training and that's it. Your model is now built. Any software developer can do this without the need to know how to build these algorithms. Currently, about 70% of ML problems can be easily solved using these high-level built-in algorithms. This number is increasing over time, leaving the 30% which is required a custom-built model done by our data scientists. It's a trifecta win, as our data scientists love to solve hard challenges, and our software developer get to learn machine learning, and finally the business scales AI production cost effectively. So, democratization of data science skill is now ticked. Okay, I have now shown you how we are scaling up our AI cost effectively. We are still halfway through this journey, and I believe there are new and unknown challenges to be solved. But I believe our awesome team who has been working hard on this will overcome them. So stay tuned for our update. Thanks for watching. You can reach out to me on LinkedIn, GitHub, or Medium blog, and join our MLOps ANZ group on LinkedIn to discuss and share any MLOps related topics.